It's okay like this? That one, okay. Hi everyone, Jérôme Saint-Louis from HRA, and today I want to talk to you about DGGAL, but we don't yet see the slides on the screen.
How to pronounce this?
DGGAL, or however you want to pronounce it. All right. Yeah. So a quick overview about what is DGGAL. So it's an open source library, high performance, written in the EC programming language, which is a superset of C. It's just compiled in native to implement multiple discrete global grid reference systems. And this facilitates the implementation of the new OGC API DGGS standard, which was recently published. And there's bindings available for several programming languages, including C, C++, Python, Rust, Java, and JavaScript. And so the easy way is pip install DGGAL or npm install DGGAL if you're in a JavaScript environment. And so the JavaScript can work both in the Node.js and in the browser environment as well. And essentially, the core library is compiled to WebAssembly, which makes this easy. And so we have a GitHub repo. It's github.com/HRA/DGGAL. If I get a few stars from this presentation, I will be very happy. Thank you very much in advance. So the DGGRSs that are supported, there's 18 of them. So the first one is very simple. It's called the Gnosis Global Grid. There's also an OGC 2D tile matrix set, which is called the Gnosis Global Grid. So it's exactly the same thing. Which means that it's also, you can also use it with OGC API tiles. But this is basically the DGGRS concept. And maybe I should explain what a Discrete Global Grid Reference System is. So basically with the OGC terminology, the latest abstract specification version 2, the DGGS means more than a mathematical structure. It's also the system that implements all the software. And it could support multiple different grid hierarchy. So now we have a new term called a discrete global grid hierarchy, which is a set of multi-resolution grids that together form this grid hierarchy. And if at this point you don't yet have, the zones don't have a name yet, so if you combine this with the zone identifier reference system, then that gives you a discrete global grid reference system. So now you could use the URI of the DGGRS and a zone ID, and you have a very precise zone boundary on the surface of the Earth at a particular resolution. So the Gnosis Global Grid, it's quite simple and it's very fast because there's no projection involved. It works directly with latitude and longitude, and it's all the zone geometries are WGS84 bounding boxes. And despite the fact that it's not equal area, there's a logic in there that tries to maintain approximate equal area. So the maximum variance is about 50% from the median area. And the other thing is all of the zones at a particular latitude band, they have exactly the same area. And it's also quite simple to compute the exact geodetic area on the ellipsoid because it simplifies because the boundaries are two small circles, two parallels. Yeah, so that's one grid we support. That's the simple one. The code is actually very, very simple. Things is a lot more complicated with hexagons. So for the hexagonal and the rhombic grid, we support, so by the way, all the other grids below are all fully equal area on the surface of the ellipsoid, with the exception of the 12 pentagons in the case of the hexagonal ones. So the next projection is the icosahedral vertex-oriented equal area, which is actually the equivalent one to the dodecahedron Snyder equal area that Felix talked about yesterday for A5. So it's actually just two ways to unfold the Earth, but the projection is exactly the same. It's just, well, that is the inverse projection to the surface of the Earth is exactly the same. But if you unfold it onto the net of the dodecahedron versus the icosahedron, of course, you have a different map. And actually, the distortion will be a little bit different. But the reverse projection to the ellipsoid is exactly the same. So we have three choice of these equal area projection, icosahedral equal area projection. One is IVEA, which is this one, which yields the best result in terms of compact zones, so zones that best approximate the circle. And then we have the IVEA, which is the classic Snyder applied to the icosahedron. And then we have the Rhombic Triacontahedron version. And actually, these three projections, they all work with the exact same method, except there's a different choice of vertices from which the great circles map to straight lines. So if you just change which vertex you pick to trace the great circles, you get these three different projections. So that's why we support all of the type of tessellation on all three, because the code is actually all the code is shared between these projections. And for all three of these projections, we support the 4R, which is aperture 4 rhombuses, so rhombuses that divide in 2 by 2, rhombuses that divide in 3 by 3, that's the 9R, hexagons that there's 3 times more hexagons at each level, that's the 3H, and the 7H, which is the same refinement strategy as H3, which is you get 7 times more hexagons at the next level. So those are the kind of the 4 choices. And for the 7H, we also recently added support for the Z7 indexing, which is basically equivalent to the IGO7 that Alexander described in his presentation this week as well. So there's some interoperability there with what DGGrid generates, and DGGAL if you use the ICS 7H Z7. So that's kind of an interoperable grid, which is maybe one of the first more complex hexagonal grids, which shows this kind of interoperability between 2 different libraries generating the same grid. And then we have the HILPIX support and the RHILPIX. So HILPIX, so it's a special projection, which is basically a combination of 2 different projections with a different one for the polar region. And RHILPIX is basically, it's based on HILPIX, but the triangles are combined together so that you have 4 triangles making up 1 square in the projection. But when you inverse RHILPIX on the surface of the Earth, you get actually different shapes, triangles, circles, parallelograms. But in the projected space, they're all squares. So it's quite simple to work in the projected space. And they're all equal area. But depending on the use case, the different shapes might be a problem or not, it depends on the use case, right? So that's why we offer all this choice of different grids. And the idea with the library is you have a single API that will support all of these different types of grids. So this is the Gnosis Global Grid here, how it looks. So you can see basically at this level 0, we start with 8 zones, and then you divide in 2 by 2, except if you touch the pole. So the result is at the north and south pole, you always have exactly 4 tiles. So it kind of approximates the equal area. And on the right, you can see sort of how we can encode the data. So basically, all these squares is basically we can encode 1 value for all of these small squares. And when you basically you project it or in a 3D globe or in a projection that maintains equal area, you'll see that it's actually quite close. And on the right, we see basically it's a building there from OpenStreetMap where basically we list the zones inside, but we use zone compacting. So basically all the zones that are fully inside the parent are replaced by the parent. So that's some of the functionality that the library support for all the different grids, as you can compact and decompact the zones. And this is what ICEA 9R looks like. So you can see basically that's the net of the icosahedron on the left. And you can see sort of the zone IDs and how it's divided here at 3 by 3. So the small squares here are level 1. And you can see again the data and the compact zones, what that looks like. And this is the 3H. So you can see, I think this is level 2 here, if I'm not mistaken. And you see some Sentinel-2 data. So that's a data packet of Sentinel-2 data using the concept of subzone again. So I'll talk a bit more about subzone. The idea of subzone is You have a DGGS client that first selects what big coarse zones are available in the region of interest, which might be the current view of the software. And then it goes and it fetches a data packet for each of these big zones. And the data packet consists of basically a set of values for all of all the zones that are inside the bigger zone. And again, that's the compact, decompact with the 3H mode. So yeah. So in the projection here, so this is the projected space that you see here. So the hexagons are all, and even the pentagons, you can see that the pentagons, like this one over here, you can see it's actually a hexagon, but because it's basically cut by the interruption, and the interruption is basically the edge of the icosahedron. So because it's missing a piece, then it becomes folded into what we call the pentagon. But yeah, so you can see these are all exactly equal area, and they all also exactly equal area on the surface of the Earth. But with the IVEA projection, some of these edges, they start to get very sharp angles, and I'll show this, for example, here. So I don't know if you can see from far, but if you look, for example, here, you can see this very sharp change of direction. So this happens near the icosahedron edges, basically. And the advantage of IVEA 9R, which again is just a simple choice of which vertex from which to draw the gray circles, you avoid this and everything is very smooth, which is why the IVEA projection is really superior in most ways to the ICL ones. And it's just a small different choice. And like Felix said yesterday, it's also even Snyder in his original paper from 1992. So already mentioning that the dodecahedron has superior results to the icosahedron. It's just that like you see here in this picture, it's easier to trace to draw the edges of the hexagons in this when you unfold it to the icosahedron. But there's actually, the trick how we implement this is basically we can map whether we do one way, the choice of vertex one way or the other. There's an easy way, and it's an affine transformation that allows you basically to still work in that space. So you can still draw your hexagon this way, but do the projection math in the other, from the other vertex. So you get all the benefits. It's easy to build a grid, and it's easy, you get the better projection. So that's kind of one of the big innovations for DGGAL to do this. And you can see it again with the 3H. So you can see like these hexagons here that look very concave. And if you compare with the, I can't even tell which one it is here, right? So I think it's this one because it's very, very smooth. So you get rid of all these not so nice artifacts. So every hexagon really looks like a hexagon. It's only the ones that are right next to the pentagons that they have this little curve. But you see here, it was a very sharp angle here. So that's kind of the big advantage of the IVEA. And maybe it's even more pronounced when you look at the 7H grid. So you can see the pentagons here that has these very sharp turn. And that's because the 7H, they have a different small rotation. I think it's about 20 degrees or so. So it's very noticeable here. And again, you can see with the IVEA 7H, it's all very, very smooth. So how can you use DGGAL? So there's docs, dggal.org/docs. Most of the functionality is implemented in the class called DGGRS. So that's the main documentation page. And there's examples in several programming languages. Like I said, there's C, C++, Python, Java, JavaScript, Rust. I think I forgot to put Rust in the first page, but there's also Rust bindings for DGGAL. And then there's also a notebook, a Jupyter Lab notebook that implements a very basic OGC API DGGS client that goes and connect to the server, fetch the data, and then present it and convert it to GeoJSON, and then use some existing tools to present those GeoJSON and with styles. So maybe now I give you a very quick overview of OGC API DGGS Part 1 core. So it's published, it's an official OGC standard. And there's three requirements class. The core is mostly about describing which DGGRS you provide and information about each zone, which Really, the client's actually not supposed really to use this at all. It's more for exploring, for debugging, for explaining the concept demonstration. But the clients should not have to ask about the information about the zone, because the idea is the server and the client, they share an understanding of what the DGGRS is, which is very similar to the 2D tile matrix set in OGC API tiles and WMTS. So the server and the client, they might both use DGGAL, for example. So they can use DGGAL to ask, what is the zone, what's the geometry? So they have this shared understanding, which can focus on very efficient data exchange requests, right? So the /DGGS is you list the DGGRS available, /DGGS/DGGRS ID. That's a short description of the DGGRS, which will link to a full definition. And the definition is something that we're still in the OGC trying to develop. It's based on the topic 21 abstract specification, but we're still trying to make sure it can support all the possible DGGRSs. For example, we discovered some new thing with the 7H, with A5. So I think we made some improvement to the schema. So we want to make sure it can describe any DGGRS that people are using. It's really, the API is agnostic of any DGGRS. And then, the get /zone ID, that means you get information for a specific zone. But again, that's more for debugging or experimenting, not for a practical client, because the client should already know this information from its local library. And then another thing we have is, the core, basically everybody has to implement it, but then a server can decide whether to implement either data retrieval or zone query or both. So data retrieval basically means give me the data inside the zone. So that's basically more detailed. Normally it's not like a single value. You could do a single value, just give me one value for the zone, but it's not a very efficient use of bandwidth, because you'll keep making so many requests for every small zone. So the idea is you ask for a big zone and you get a data packet for a lot of things inside the zone. So that's the data retrieval. And the zone query is basically tell me which zones for which you have data, or you can have a more complex query that uses SQL2 that will say, give me the zones where elevation is greater than 3,000, for example, or it could be an even more complicated SQL2 expression. So that's the basic, very quick overview of OGC API DGGS, but please take a look at the standard. Quick, how to use DGGAL in Python. So initialization, there's a couple extra steps, because it's all built on the EC framework, and essentially the app is the EC, instantiating the EC environment, and then setting up PyDGGAL. So it's 2 small extra lines, and the idea is you can share, if you use other EC libraries, you would use the same application construct, and all of this works together. So that's the small step to set it up. And then to create your DGGRS, you just say DGGRS equals the name of the DGGRS. So in this case, I instantiate IVEA 3H. And then the idea here is taking some extract from the tutorial that you can see in the Jupyter notebook. So basically, you have a map, the user pans, zooms. Now you have a zoom level, and you have a bounding box. So you compute the bounding box, and then you tell DGGAL, give me all the zones inside that bounding box. And you say at which refinement level you want those zones. So for example, you say refinement level 7 in this particular bounding box, give me all the zones. And then if you get these zones, then you can get the ID from the zone. The internal identifier for the zone for the library is a 64-bit integer. Now you can get a textual ID, and that's what the API DGGS use. And then you would make a request for the data. And then, for example, if you request it in the DGGS JSON format that I'll talk a little bit about, and then you could say, now I want to convert it to GeoJSON because my client can only display GeoJSON. So that's what this is doing here. And how do you do this conversion from DGGS JSON to JSON? Again, you can work backwards, get the zone from the text ID, and then this is the concept of subzones. You say, give me all the subzones inside this zone at this depth that I requested, or at the depth that's identified inside the DGGS JSON. And then for every subzone, you can ask the library what is the geometry for this zone. So it will give you the list of vertices, which are refined because most of the IVEA, ICEA, RTEA, the zone edges, they're not great circles or anything, so you really have to get smaller vertices along the edges to trace the proper zone boundaries. So that's the idea. So this is some example of zone data requests from Sentinel-2 and GEMCO data. Also, so the DGGS JSON is for vector data, and there's also DGGS JSON FG, which is based on the OGC features and geometry JSON, which is also a superset of GeoJSON. So the idea with this format is you don't rasterize the whole thing. You just convert your geometry. Everywhere you have like a coordinates pair that becomes an index into the deterministic subzone order. Yeah, that's the basic idea. So this is an example here. What are the zones from this collection and the ICEA 3H DGGRS at resolution level 10 within this bounding box? So it returns you the data, and it's an elevation model in this case. Now this is the idea here of what are the zones inside a parent zone. So you can get all the zones inside of a specific parent zone. Still have a... -2 minutes. -2, okay. Okay, I thought I had 25 minutes, but okay, quickly. So some more example. This is an example again, data encoded in DGGS JSON, just to show you here how you see this is an example of DGGS JSON FG, where the coordinates are replaced by a single subzone index. And that's pretty much it. So no time for questions, but you can come to see me.
No, well, now we have time for questions.
Okay.
Yeah. Yes, does anyone have any questions? Yeah.
Thanks a lot for the overview. For the JavaScript stuff, now we have seen now a couple of really cool visualization libraries like Longboard, DGGAL, and so on. PepLibre. How easy would it be to use the JavaScript WASM to like link those as like plugins or something like that?
It should be very easy because I've already done it, for example, with open layers. And if I can show you the small web demo of the web. So if you go dggal.org/web and you have the demo here, and for example, I think it's still loaded. Yeah, so by default it's IVEA 7H, and then you do query, and then you can see it uses DGGAL to get the polygon, and then it uses open layers to display it. So yeah, if you go to dggal.org/web, you can look at all the example JavaScript that uses this, and it should be easy to use DGGL or any other library. And yeah, I guess that the thing I also wanted to mention is the great tools that Tang has been building. So if you look for VGrid and QGIS, you can find the VGrid plugin. Basically, you can use DGGAL from QGIS from the menu is very easy. And he's got the MapLibre plugin too using DGGAL. So he's already doing that sort of thing there in JavaScript. Thanks.